So now that we have seen why we need a concept of limit, we are going to try to go over the definition. So we want to define the limit of a function, say g, as x is approaching a. And we have seen that this limit should not depend on the value of the function at a, precisely because we want it to apply in particular to this kind of function that is not even defined at a. So let's take a look at an example from the graph. We may ask the question, what is the limit of this function when x is approaching 3? Well, obviously there's two reasonable candidates, 5 or 7. What should be the limit of g when x is approaching 3 is the number, if any, that the values g of x approach as x gets closer and closer to 3, but really not equal to 3 because of the observation we made before that this should not depend on the value of the function at 3. Therefore here the limit ought to be 5. More formally, the definition of the limit of a function g at a point a is the value L, if any, that has the property that the values g of x can be made as close to L as we want by taking x sufficiently close to a, but not equal to a. So what does that really mean? Let's get back to our graph and let's try to interpret this definition for this function where the limit when x is approaching 3 is 5. So what does that mean? That the values g of x can be made as close to L as we want. As close to L. Let's say for instance we want the values g of x to be within 0.5 of the limit 5. That means we want the values g of x to fall within this horizontal band. In other words, we are looking at the parts of the graph that fall in that band, and we see that for these values of x, g of x will be indeed between 4.5 and 5.5. How do we want to achieve that? According to that definition, by taking x sufficiently close to a. Well, in other words, what happens over there, we don't really care. But you see that indeed, we can achieve that by taking x sufficiently close to 3, but not equal to 3. In other words, all the points in that red interval around 3 are mapped by the function g between 4.5 and 5.5, except possibly 3. Now what we want is to be able to do that for any distance we fix, right? Here we started by saying we want the values g of x to be within 0.5 of the limit 5. We could have started with within 0.1 or of the limit 5 or within 0.001. If we pick another distance, we should be able to find some interval around 3, except possibly where all the points except possibly 3 are mapped within this distance of the limit 5 by the function g. So now we have a definition of limit. And we have illustrated on a picture how to interpret this definition, and it's good enough for us to understand what it means. However, it's not good enough to be used for formal proofs. And therefore we're going to go over the argument we gave on the picture on the previous slide. We're going to go over it again, slightly more formally, in order to derive a reinterpretation of this definition that we will call the formal definition, or sometimes epsilon-delta definition, of the limit. This is necessary only for the purpose of proving statement about limits, as we will see later. So let's go over this argument again. We want the values g of x to be made as close to L as we want. In other words, if we fix a distance, let's call this distance epsilon, or any distance epsilon that we fix, we want to make the values g of x be within epsilon of the limit L. In other words, we want g of x to fall within this horizontal band between L minus epsilon and L plus epsilon. Right, so if this is the case, then the distance between g of x and L is going to be less than epsilon, which we can write that way. Here is a part of the graph that satisfy this condition. Right? The values of g of x on that graph are going to be between L minus epsilon and L plus epsilon, and they come from values of x that are close to A. However, we want to say that we achieve that by taking x sufficiently close to A. In other words, we want to interpret that in terms of the distance between x and A. So to make it about the distance between x and A, we have to make this interval centered at A and not just around A. So that is why you have to recenter things at A. And then we can interpret it as, for that epsilon, there is a certain radius that we will call delta, for which the interval centered at A of radius delta is entirely mapped by the function g inside the interval centered at L of radius epsilon, except possibly at A, and that's why we ensure that the distance between x and A is less than delta to be within that interval, but greater than 0 so that we exclude the case x equal A. And now if we change epsilon, if we take a smaller epsilon, then we should be able to do that again. Of course, to do that again we will have to change delta. In other words, delta depends on epsilon. And now this is our new formal definition of the limit. The limit of g of x when x is approaching A is L if for every epsilon there is delta, such that when the distance between x and A is non-zero but less than delta, then the distance between g of x and the limit L is less than epsilon. The first observation, once we have this definition, is that the limit of a function at a certain value may or may not exist. Consider for instance this function, and let's say we are looking for the limit of this function f when x is approaching 1. Well, you see that near the line x equal 1, the behavior of the function is that the value becomes either very large or very negative large. In particular, if I take some interval centered at 1, any interval centered at 1, no matter how small it is, the corresponding part of the graph will never be mapped completely to an interval centered at a specific value. In other words, the limit of the function at 1 does not exist. Another way for the limit of a function to fail to exist is if the function has really two pieces. Well, in some sense it was the case in the previous example where we had a vertical asymptote, but the values of the function were getting larger and larger. Here we don't have this phenomenon, but we still have a problem to have the limit in the regular sense when x is approaching 1. You see that here, if x is smaller than 1 and we track what happens to f of x, the y values of this point get closer and closer to 0 as x gets closer and closer to 1. On the other hand, from the right, the y values of this point, in other words f of x, become closer and closer to 4 as x gets closer and closer to 1. So if I take an interval centered at 1, then I'm going to have some values that correspond to what happens on the left hand side, some values that correspond to what happened on the right hand side, and there is no way I'm going to map this interval centered at 1 entirely inside an interval centered at a fixed value. because it cannot be an interval centered at 0 or an interval centered at 4. In other words, the limit fails to exist again. So now you're ready to move to the next video for us to study basic properties of limits.